Now that we have the terminology and the skills that we need to look at the quantum mechanical systems, let's see how we would use the Hamiltonian to solve for wave functions and energies for a particle. And the first thing we're going to do is the simplest possible equation where we just have a constant potential energy. So in this system, our potential energy operator is just going to be a constant value for the potential energy. And remember that the kinetic energy operator is always minus h bar over 2m, take the second derivative. And so our Hamiltonian, that's the first thing we need to do is write the Hamiltonian, is kinetic plus potential. So it's going to be minus h bar squared over 2m, take the second derivative, plus v naught. And the equation that I want to solve is going to be h hat acting on psi is going to give me the energy times the wave function back again. And I'm going to demand that these wave functions be eigenfunctions of the Hamiltonian. So let's see how we would solve this problem. So if I take my Hamiltonian for a constant potential and I act on the wave function, I'm going to take the second derivative of the wave function plus I'm going to multiply the wave function by the potential energy operator. And that's going to give me the energy times that wave function back. So if I rearrange this equation, I have h bar squared over 2m, opposite of that, times the second derivative, is equal to, I'm going to subtract v naught psi from both sides. So I'm going to have E minus V naught times psi. And then I'm going to multiply through by a negative 2m over h bar squared so that I isolate my second derivative term. And so then I have okay. So at this point, I can see that I have this collection of constants here. And I am going to lump those all together and call them k squared. So let's think about what this group of constants is telling us. To think about this, let's think about the fact that the energy, the total energy, minus the potential energy is equal to the kinetic energy, which is 1/2 mv squared. And if I take the kinetic energy, so if I take E minus V naught, and I multiply 1/2 mv squared by m divided by m. So in other words, multiply it by something that equals 1. I haven't changed its value. So that tells me that E minus V naught is equal to m squared v squared over 2m. But m times v is the momentum, and so E minus V naught, my potential energy, or my kinetic energy, is equal to momentum squared divided by 2m. So that means that 2m times E minus V naught is equal to the momentum squared. So that group of constants, right, is 2m E minus V naught over h bar squared. And so that's equal to p squared over h bar squared. And I'm going to call this group of constants k squared. So that means that k squared is equal to p squared over h bar squared. Or the momentum is equal to h bar times k. And so this group of constants that I've called k squared tells me about the momentum of the particle. The momentum of the particle tells me about the kinetic energy of the particle. And so it's probably helpful to remember some of these relationships that I've boxed. We can go a little bit further and we can use the de Broglie relationship. So remember that de Broglie told us that lambda was equal to h over p. And so if I divide both sides by 2 pi so that I get h bar, so h divided by 2 pi is h bar, then I have this. So now if I solve for the momentum, I can see that the momentum is equal to h bar times 2 pi over lambda. And so 2 pi over lambda must be equal to k if I just make the association with my equation for the momentum in terms of k. So the other way to think about k is that it tells me about the de Broglie wavelength of the particle. And we often call k the wave vector. Okay, so if I make all of those constants equal k squared, then my differential equation turns out to be the second derivative of psi is equal to minus k squared times psi. And so I need a function which is going to return k squared and psi back again. So when I differentiate it, I always get psi times a constant. And it turns out that solutions to this are e to the minus ikx or e to the plus ikx. And you can check that for yourself to make sure that those functions for psi will give you the correct answers. When you take the second derivative, you get minus k squared times psi back again. So let's think a little bit about these functions. They're imaginary. It's a little bit weird, and you're probably not used to thinking about what an imaginary function looks like. So it turns out that these two functions are traveling waves. So they are periodic, and they're actually traveling waves. And when I have e to the positive ikx, I have a traveling wave that is traveling in the plus x direction. And when I have e to the minus ikx, I have a traveling wave that is traveling in the minus x direction. So one of these describes a particle that has a momentum of h bar k and a wavelength of 2 pi over k, and is traveling in the positive x direction. And e to the minus kx describes a particle with momentum h bar k that's traveling in the minus x direction. So in this case, the particle has momentum h bar k, and in this case, the particle has momentum minus h bar k, because momentum is a vector and it has a direction and a magnitude. The magnitude is always h bar k for both of these, but the direction in which the particle is traveling is different. So we have two possible solutions, and so the most general solution is a superposition or linear combination of the two possible solutions. And so we can write that psi at x is equal to some coefficient e to the ikx plus some other coefficient e to the minus ikx. And these coefficients will tell us what the probability is that the particle will travel in the plus x direction and what the probability is that the particle will travel in the minus x direction. So c1 squared tells us about the probability that it's going in the plus x direction. C2 squared is going to tell us about the probability that it's going in the minus x direction. So now we have our wave function, and we need to know something about the energy. So remember that the solutions to our Hamiltonian, our Schrödinger equation, are always going to give us a wave function and an energy. So we know that the energy is all kinetic energy. And that energy is momentum squared over 2m. And we said that the momentum was h bar k, so we square that, divided by 2m, and those are our energies. So we can get the energy of the particle by just squaring the momentum. We know the momentum is h bar k, and divide by 2 times the mass of the particle. Notice that there are no restrictions on k. So I haven't said anything about what k is, what it can be, what it can't be, so there are no restrictions on k, which means that all energies are possible. And so this is a system where the energies are not quantized. And what we're going to find out is that if we have a free particle, so these are free particles, that there is no quantization of energy. How do I know it's a free particle? Well, the forces acting on the particle are minus the derivative of the potential with respect to x. And if the potential is constant, then the forces are 0. So if there are no forces acting on the particle, that's what we call a free particle. There are no forces acting on it. It's free to go wherever it wants. So these free particles have energies that are not quantized. And so what we're going to find is that only particles that are confined or that have forces acting on them have quantized energies.